Hello, I'm Selin Erdoğan, master student in Middle East Technical University Mechanical Engineering Department and Design Engineer in Aselsan. I will make a presentation on a novel solar dryer for olive mill wastewater, which we have designed in scope of a TFEC project with Professor İlker Tarı. Here you can find the outline. I'll divide my presentation into parts of analytical analysis and real-life experiments verifying these analytical results. After this slide, I will leave from this camera box and let you track the page numbers in case it would be hard to bear. First of all, the main aim of this project is to find a solution for the drying process of olive mill wastewater. Olive mill wastewater is a problematic outcome of olive oil production process which contains residues of oil pastes, oil, and water. It is toxic to throw it on land as it pollutes the surface and underground water sources with its oil content. Getting rid of wastewater by leaving it for evaporation is inefficient as it takes too long because of the oil layer remained on the top. So, a dryer design powered by solar energy is proposed. Here the schematic of conceptual design can be seen. The inner surfaces here, these parts of the reverse pyramid, is heated by hot oil circulating in channels which you can see in figure 3. Here you can see the channels. Hot oil is provided from a solar energy powered parabolic trough collector. Wastewater is being sprayed from the nozzle at the top to the heated surface. Water inside this fluid evaporates when contacts with hot surface, and the remaining solid particles are collected from the bottom to a tank like that. This residue can be used as biomass. All four sides have different channel configurations for examining different conditions. Two opposite sides have lateral channels and the others are inclined. This one and this one are inclined. The oil inlet and outlet openings are opposing for the mutual sides. For example, in lateral configuration, the inlet is from the top for one side and from the bottom for the other side surface. Before production, CFD analyses were held to see if we would be able to reach higher values than the evaporation temperature at steady state or not. Temperature distributions for 4 different flow geometries were analyzed with ANSYS Fluent. Oil inlet temperature is taken as 170 degrees Celsius, which is the experimental temperature value obtained from a parabolic trough collector present. The outer surfaces of the dryer are insulated and the oil flow is inputted as laminar with a flow rate of 0.25 meter cubes per hour. The number of mesh elements was 3.5 million. From CFD results, it is seen that the lowest temperature seen on the surface is 70 degrees Celsius when evaporation takes place. The picture seen on the right part is for the ones when evaporation takes place on the surface, and the ones at the left are for the case of natural convection. The location of the lower temperature region depends on flow configuration. As the fluid accumulates at the lower part, this part of the reverse pyramid, configurations providing higher temperature at lower parts are foreseen as more efficient. For example, in configuration A, hot oil enters the parallel channel geometry from the top, from this point. Therefore, the top part is hotter and it gets colder as the oil circulates and transfers its heat. Therefore, the temperature of lower surface is lower. The condition is opposite for case B, where the oil enters from this point, from the bottom. The steady-state temperature for most of the vertical direction, this direction at the bottom, is higher than 100 degrees Celsius. The lower temperature regions are the ones that sprayed water might not even reach, these parts, because of the conical geometry. In configuration C, inclined geometry with inlet from the longer channel from this point, the temperature magnitudes are similar to the parallel configuration, but the distribution has a direct relation with the flow path. Again, lower parts have higher temperature than configuration D, so a better performance is expected. As the region which our fluid mostly falls is this lower part, flow geometry B is expected to be the most effective flow configuration. Experimental setup and produced design can be seen in figures. On the left, you can see the parabolic trough collector simulator, which simulates the heating of oil with solar energy. On the right, you can see the dryer design. Here, water is sprayed from the nozzle at the top from that point. Hot oil coming from the parabolic trough collector simulator is pumped to the four sides of the dryer separately. And this is the setup while the nozzle sprays down the water. Here you can see the conical geometry of the sprayed water more clearly. This is the table listing the nozzles we have used in the experiments. We tried for different spray angles and flow rates with 6 different nozzles to examine many conditions. The experiment results are collected as a temperature distribution of evaporation surface with an infrared thermal camera. With this nozzle, the first one in this table, a water flow rate of 1 liter per minute is provided with a spraying angle of 53 degrees. In all experiments and all configurations, left and right corners of the upper region stay at high surface temperatures since they are at the regions where smaller amount of water droplets can reach. That is due to the conical spraying inside of a cornered square pyramid. In C, which is the inclined geometry with inlet from the longer channel, the thermal camera images are taken from the side because of lack of space during the experiment, and that's why the picture is tilted. For all configurations, the temperature goes down as the sprayed waters flow down because more water is accumulated at the lower region. The part that cannot evaporate flows down to the lower regions. These regions have lower temperature, which might be problematic during the evaporation because the evaporation rate goes down. This effect can be seen significantly in these inclined geometries. We can conclude that the performance of inclined flow is worse than the lateral one from these pictures. With the second nozzle at the table, volumetric flow rate is 1.5 liters per minute and spraying angle is 59 degrees, which is greater than the angle for the previous nozzle. Higher angle leads to a higher fluid boundary location. Here you can see the fluid boundary location, and you can conclude that it has a high altitude. Because the flow rate is greater than the previous nozzle case, average temperature of heated surfaces are lower in this case. Inclined geometries again show non-uniform temperature distribution characteristics with insufficient temperature value at the bottom of the reverse pyramid, where all the unevaporated fluid flows with gravitation. And this nozzle has a volumetric flow rate of 2 liters per minute and a spraying angle of 46 degrees, so the droplet regions are less. Because of high flow rate, more scattering of droplets can be observed at the upper parts of the fluid boundary on the surface. We can observe higher average surface temperatures than the previous cases with this nozzle because of the smaller spraying angle, causing a smaller area for the water to contact. So there is a small area which heat is taken from the surface. With the fourth nozzle, a flow rate of 3.1 liters per minute and a spraying angle of 59 degrees is obtained. There is an inconsistency of the sprayed fluid boundary of the surface and the nozzle angle. From the image, from there, it seems like the angle is too low compared to the previous nozzles. However, the previous nozzles had lower angles. So with this nozzle, we expect a greater fluid boundary, a greater altitude of fluid boundary. As we can observe it for all channel configurations, we can conclude that this might be caused because of a problem like a blockage in the nozzle. And when images A and B are compared, it seems like one side gets sprayed fluid with a higher angle, this side, and this might again be caused by blockage or misplacement of this nozzle. So there might be an experimental sourced error with this nozzle. With the fifth nozzle, flow rate is 3.6 liters per minute and the spraying angle is 46 degrees. The temperature profile patterns are similar with the previous nozzle, having the capacity size 2 as the spraying angles are same, but the overall temperature in this case is lower. It is reasonable since the flow rate is greater and more heat is taken from the surface with more sprayed water per unit time. With a spraying angle of 59 degrees, 5.1 liters per minute water is sprayed with the last nozzle alternative. Lower temperatures are observed on the surface as the flow rate is high. Sprayed water covers greater heated surface area with the high spraying angle. More surface area is involved to the evaporation process. At the regions where channel turns are present, here you can see in these regions, heat transfer is higher because of the irregular flow pattern at these curves, and these regions have higher temperature. To sum things up, the inclined channel geometry is observed to be less effective than the lateral channel geometry in both CFD and experimental results. In lateral configuration, the configuration having the inlet from the bottom showed better performance as it had the advantage of having the high temperature region at lower part where fluid falls mostly. And nozzle having larger spraying angle showed better performance as the evaporation surface is higher and a greater amount of wastewater can be dried. Here you can see the references we have used in this presentation. The financial support for this work is provided by TÜBİTAK, which is a great research council providing support for many areas in Turkey. And here you can see our contact informations. If you have any questions, you can ask directly now, or you can email us or contact us from these addresses. And thank you for listening.